Welcome. This module, computer simulation and modeling. So we did dimensional analysis, we did calculus, and now the new module is computer simulation and modeling, where we will build basically on what we learned in the calculus module, specifically differential equation and all of them, integral calculus, for example, because if you remember, if you have a differential equation, you solve it with integral calculus. Yeah, and I will show you numerical solution also, which based on ideas also from differential calculus, like Taylor series and so on. Okay. Uh, these are some references. Mainly, this module will focus on also numerical solution because a lot of the differential equations that typically for real life application, the differential equations that you will have, it will not have an analytical solution, and you need to solve it numerically. So in this module, big part of it will focus on numerical solution to see how you can solve the equation numerically also in case no analytical solution exists. Okay. And if you want to learn more about numerical solution, you can check your textbook, which is Numerical Method for Engineer, and that's where you'll find a lot of numerical solution. Part of this numerical solution we will be covering in this module. Also, you can check Groundwater Project for a lot of free books on these topics. Okay. So two lessons in this module, in Introduction to Physics-Based Modeling. I will basically introduce main concept in physics-based modeling, starting from defining the model purpose, developing your mathematical model, and then once you develop your mathematical model, you have to solve it either analytically or numerically. So I will just introduce this two concept in this lesson, and I will give you an engineering application. I'll show you some example like how could to formulate a mathematical model for the problem of your interest and how you can attempt different solution methods. Okay. And then in lesson two, lesson one is just an introduction. Lesson two, we will start to look at some details of these mathematical models, like boundary condition. What are the different type of boundary condition? And then we will look like once we have a mathematical model, how to solve this numerically. And specifically, we will look at finite difference method. Finally, we will cover inverse modeling or model calibration. So you set up your mathematical model, and then you set up your numerical model, and then you run your model, and after you run your model, sometimes or often the case you would need to calibrate this model before you use it in your application. So we will also talk about inverse modeling. Okay, so let's just start with lesson one, Introduction to Physics-Based Modeling, and part one would be the mathematical model. So, in the objective, by the end of this video, you should be able to understand the role of mathematical model in engineering problems or uh, solving, and describe key step in developing a mathematical model and formulate a mathematical model. Like we will formulate this mathematical model for a very simple like engineering problem, just to learn how to drive our mathematical model from physics principle. Okay. So advanced engineering analysis, it involves physics-based and data-driven model. We look at physical models already and how to develop a physical model for your prototype. We did this in module one. We in this module we will basically look at physics-based models, which are generally based on differential equation or algebraic equation or something of that form. Uh, then there is other types of models that we also use in advanced engineering analysis. These are data-driven models, and these data-driven models, these are covered in another course called environmental data science, where it's mainly focused on data-driven techniques. And of course, you could have hybrid, yeah, physics-based and data-driven. You can have a hyper of these two. Okay. So this is module one. This is module like two, three, and four is a calculus uh, module, and this is in another. Okay. Let's just start with very basic, like just basic question, like why do we even need a model? Why a model is important? So let me ask you a question. If I asked you how much load is needed to break this table, how are you gonna answer this question? So somebody gave you this task. He told you how much load do we need to break this table. How are you gonna answer this question? Well, there are two ways of answering this question. One way is that you actually start like loading this table. So you can start you can start actually putting some loads on this table. You start like loading the table, yeah, and you keep loading the table. Like so, you put some loads in the table. I mean, they are not enough. You increase these loads, yeah, you increase this load, and you keep doing this until the table breaks. Then that's one way to answer. But then, if you were asked, okay, like these loads that you use were like distributed load. What if these load were not distributed load? Like what if these were not distributed load, but these were like point loads? So if I want to put like one load here, for example, and one load here, and one load here, and one load here, then how much load do you need? Then you do the same. You keep just increasing this load until the table breaks. But then if you got asked another question, what if these loads were not at the corner, but maybe just here in this part, in the middle? Yeah. How much load then? Like two in the middle in this scenario, like giving this scenario, how much loads in you? Keep loading until the table break. But again, you see the problem. This is tedious, and you so and you can have like so many scenarios, and you'll be breaking so many tables. But an easier way, or like not an easier way, like a different approach for doing this is actually to create a model. Yeah, to create like a model for this table. And then like you can use this model, you can bring this model, like create a model for this table on your computer, and then you can use this model, and instead of doing this experiment like in situ, you do this experiment on your computer, and then you can try not only three or four scenarios, you can try as many scenarios as you need, because you just change these loads on your computer, and then your model will give you the answer. For other system, like this table is just something like you can do this experiment in your lab. But for other system, like for example, like you are talking about a groundwater system, which is not, and that could, an aquifer could be deep, it could be very spatially cover a big spatial extent, like that could be like a county or even a whole state, yeah, or local, like it have different scales. So it doesn't make sense to make experiments in the field uh, at especially like a larger scale. And in that case, what we generally do, we bring this aquifer to our computer, and then we do all these experiment and different management scenario and different future scenarios on our computer. Yeah, on like we create a computer uh, model. But to do this, like to do this mathematical model, or to come up with this computational model for your system, what do you need? Well, you need to understand your system, because if you don't understand the physics of the system and how this system function and the relationship between like the material. So here, for example, you have different things. You have a structure. You have, so the structure like would be like the shape, like that structure here. Yeah. You have dimensions. Yeah. Like these are some dimensions. And then you have like material properties, like the material properties of this wood, for example. And then you have the load, the property of the load itself, the forcing, your forcings. And then you have the physical relationship, like you need to find the rate of a change of like the stress of the material as you apply this load, and the material internal resistance or relaxation. So you need some physical equation. So you need to understand, like if I understand something, then I can model it. If I don't understand this physical relationship and how this physical equations that I have, like the equation of like forces, for example, so or stress of the material, like how stress is it changing, like as a function of time and as a function of other forces and as a function of dimension and other forces. If I don't understand this relationship, and if I cannot put it into an equation that would represent my system behavior, then I cannot model it basically, or this model will not answer my question. Yeah. So here, when you do like this model, basically you will have like a dependent variable, like the dependent varia- variable, dependent variable. And in that case, for example, your dependent variable could be like stress or displacement or whatever. Yeah. And that is like a function of your independent variable, your independent variable. And in that case, your independent variables will be like time, position, and things like that. Something that has to do X, Y, and Z and time. That would be like your independent variable. And some parameters. Like in that case, for example, parameters could include the material properties and the forcing function. Like the forcings. For forcings. We call it forcings. Like forcing function or forcings. Okay. So basically, yeah, the forcing in that case, for example, would be the applied load or temperature or whatever. Yeah. Uh, okay. Temperature could be also a parameter or a forcing depending on what you are doing. But that's the idea. Like so, that's basically like if you understand this relationship and you can put it into mathematical equations, then you have a mathematical model. And now, once you have a mathematical model, this mathematical model could be generally in the form of a differential equation, an ordinary differential equation, or a partial differential equation, or simply an algebraic equation, yeah, depending on what you're doing. And then you solve it, yeah. Okay, so basically that is the main idea. Like, why do we do this physics-based model? Because we want to have a computational model on our computer so that we can conduct these experiments on the computer instead of conducting this experiment like in situ, like or using the real system. Yeah. So here we said like we can answer this experimentally and mathematical model. And the most important thing to understand about like these mathematical model is that like in order to develop a model for your system, you need to understand your system. That's the most important thing. So if I understand something, then I can model it. If I don't understand something, then I cannot model that system because I don't understand it. I cannot put it into equation. I don't know its parameter. I cannot don't know its forcing and so on and so forth. Okay. So here, this is would be like again an example of a mathematical model. Like you have a dependent variable, you have an independent variable, you have parameters, and you have forcing. So here, for example, let me show you. I have an equation here. So governing equation, you already are familiar with these type of equations. So here, for example, I want to see heat transport in this rod. So you have a rod, yeah, and I want to know about heat transport in that rod. Okay, like how heat is, oops, how heat is like transported, like in 1D, yeah, in that rod, yeah, moving from here to here to here, yeah, how heat is transported in that rod. So here, what would be my dependent variable? So that would be temperature, because that will be like how temperature is changing. Yeah. So you have like you apply some temperature here at this boundary and some temperature here at this boundary, and this rod will have some initial condition, and then temperature here will be changing with time. Yeah. In space and time, temperature will basically be it's changing in space and time. So that would be my dependent variable. What is my independent variable? That would be like time and space, like how heat is moving in space along my domain and in time. Yeah, and we've seen this differential equation before. And some property, some of this is like thermal diffusivity, for example. It measures the rate of which temperature change within the material. So you have here this alpha here, this is thermal diffusivity, and that will depend on the material. For example, the thermal conductivity of the material, it will depend on the density of the material, it will depend on the specific heat capacity of the material, and so on and so forth. So that's like a parameter. Yeah. So this guy would be like a parameter. Okay. And then forcing. What would be the forcing? So the forcing would be, for example, my boundary condition, like what is happening here, like uh, so if there is like a constant heat source here, for example, or this boundary is insulated, there nothing is allowed to escape. Yeah, so if this boundary is insulated, means no flux, zero flux. That's like would be second type of boundary condition here. If constant heat source and the temperature here is constant, that would be, for example, the first type boundary condition. And we will talk about boundary condition and different types of boundary condition in the next lesson. Yeah, but that's basically like the idea. So you're forcing here would be like your boundary condition. So here, like boundary condition at x equal to 0, and at any time I have like T1 here, so I have a constant temperature here, and here at L, x equal to L, so x equal to L, and at any time I have like another constant temperature here. Yeah, and basically, so I have a constant temperature here, or like T2 and T1 here, and that would be my forcing. And then also I need another information, if, especially if this is in a transient state, not in a steady state, is like the initial condition. Because if in a steady state, you don't need the initial condition because it will converge to this condition anyway. Uh, but in the transient state, you would need to know the initial condition, like because if this is very cold, ice cold versus boiling hot, yeah. So this is the initial condition of your system. Okay, so that's basically a mathematical model. You see here, the mathematical model here is taking the form of a differential equation, a second order partial differential equation, And this differential equation, if I was able to solve it, it will basically tell me the temperature across the space, like temperature here, temperature here, temperature here, temperature here, temperature here, and temperature here. And not only in space, but in time, how this temperature is changing in time. Yeah. If I was able to solve it either analytically or numerically, then I could then I could learn about my heat. Yeah. That's very useful system, by the way. Like for example, in engineering application, if you learn about like how heat is changing in space and time, that's basically how you design a geothermal energy system. Yeah, you use an equation like this. Yeah, and that's how you design these systems, and operate them also. Okay, but anyway, so steps in mathematical modeling. So the first step in the first step in modeling in generally is that like you define your problem. So you clearly state the engineering problem, including like the objective, constraint, and desired output, because there is no such thing as one model fit all solution, like one model that could answer all the question. You design the model for a specific purpose. So before you do any modeling activity, you say, okay, what is the purpose of this model? What question will this model answer? And based on the questions that this model will answer, you will start developing your model and simplifying assumption accordingly. Because once you know the question, you just find the variables or the relationships that are most relevant to this question. Other variables and relationships that are not relevant to this question, you don't want them to include it in your model because you want to keep your model as simple as possible. Okay, so the first step is you define like the problem definition and then system simplification and assumption. So basically, you just based on the definition, problem definition, you start to simplify the system. So for example, I can here neglect if I just want to see like the temperature here. Yeah, if I here, one simplifying assumption, for example, I could neglect here loss to the surrounding. If that is uh, defining like a geothermal system, for example. Yeah, I could, for example, assume constant thermal property if that is a valid assumption. So I could thermal conductivity, specific heat capacity, the density of the rod, I can just assume that this is constant. So if that is constant, then I can bring this guy out. So this guy is not changing with X anymore. So I can, if that is like a relevant assumption, I could assume 1D heat con- uh, uh, conduction or advection and dispersion, which is called like heat conduction, along the length of the rod, like one-dimensional heat transfer. So I could ignore, for example, radial or circumferential direction, for example. Okay. I could neglect any heat generation within the rod. I could neglect any. I could assume that this cross section area is constant. It's not changing. So you just need to make this assumption based on your problem definition or your modeling definition. I could ignore, for example, surface roughness or minor defects, where small surface imperfection have a minor impact or loss of conviction. So I could do something like this if that is a valid assumption. Versus, for example, if I'm designing a telescope, that huge telescope that will get me like very far away in the space, that might not be a relevant assumption. For example, that I assume that my surface is like surface imperfection or might have a minor impact or on heat loss and things like that. That could be, for example, an invalid assumption, and then I need to include like a relevant assumption and I need to include this in my model. But for designing a geothermal system, I mean, you can, uh, that wouldn't be valid. I mean, that could be like a simplifying assumption, yeah. But anyway, so you define like the system simplification and assumption, and then you formulate your model. So here, giving these assumptions that like this uh, thermal properties are constant, I was able to get like this guy out of my integral. So instead of having like d over the x, like alpha dt over the x, yeah, is equal to dt. Yeah, I was able to get this out of, because this is no longer a changing in space. This is constant. Okay, and here there are some constant here. Yeah, just there are some constant here. This equation. Okay, uh, or you can just like include it all here. This guy. Okay, so I can just like include this in my. I can assume that this is constant. Okay, so you formulate like you do your simplifying assumption. You formulate your model, and then you solve your model. And this model you can solve it either analytically or numerically, as I will show you in the next video. Yeah, and then after you solve your model and your model is running, you need to calibrate these models. So, for example, how to calibrate this model? Model calibration means that you need that whatever your model is simulating or producing, it should match what you are observing in the actual system. And to make the model match with the actual system, you need to calibrate the parameter of your model, like your uh, alpha, for example. That could be one parameter. You keep changing alpha until your model is what your model is simulating is what you are observing in the actual system. Okay, that this model is calibrated. Once the model is calibrated, then you can use it for your intended application and so on. Okay, so let's formulate a, a simple, like let's apply this, like let's apply what we just learned to a simple engineering problem, which is formulate like a mathematical model for a free falling parachute. So like you have this guy and he's like falling with a parachute, and you can formulate like an equation either before or after he opens the parachute. I mean, it doesn't matter. I will, because that will be captured in the parameters of the problem, as I will show you. But for any of these cases, you need to be able to understand the main this system, yeah, this physical system. So when and the governing equation of this physical system. So obviously, the governing equation of this physical system would be like Newton law. It's a balance of force, because when this guy is falling, what is happening here? There would be like, oops, there will be like a force that's applied here. That would be the force of gravity. So basically, like the guy will, you let anything fall, like in a free fall, the gravity will be pulling it down. Yeah. So this is the force of the gravity. Yeah? Something falling. Yeah. But in opposition to the force of the gravity, once he opened his parachute, or even without opening his parachute, there will be some also drag force. Yeah. So that would be, so this is the force of gravity, and then this is drag force. And the so Newton laws tell us that if these forces are balanced, then like the sum of these forces is zero, then that system will not be accelerating. Like, so this guy will not have any acceleration. But if these forces are not balanced, yeah, then there will be acceleration. So if these forces are not balanced, then there will be acceleration. And this guy would be, there will be some force of acceleration, either like accelerating up, downward, or upward. And in that case, it will be uh, mainly downward for most of the time. It might be upward a little bit when he start opening his parachute, yeah, but most of the time it will be downward. Okay, so now I have a governing equation actually. I have like the sum of the forces is equal to mass time acceleration. So I have a drag force here and I have a gravitational force here. Okay, so sum of the forces, that would be my drag forces, yeah, plus my gravitational forces, that's equal to mass time acceleration. So I have actually, I started now to develop my mathematical model. Uh, I know this guy, yeah, gravitational force. That is easy, yeah, because that's mg, mass time gravity. So that's my gravitational force. I know acceleration, yeah. So acceleration, that would be like dv over dt, like the change in velocity with respect to time. Yeah. How about this guy? What is the drag force? Well, I don't know the drag force, so you can just start by that requires experience. That's why I told you you can. If I understand the system, then I can model it. If I don't understand the system, then I cannot model it. So how could I model this drag force? So you can start by a simple assumption. You can say like, okay, my drag force, that is proportional. So this means this sign means proportional to like my velocity, for example. Okay. Then you can say, okay, my drag force is equal to like my velocity times some proportionality constant, like a constant. And I can assume that this is just a constant, yeah. Somebody else can say, you know what, my drag force base is proportional to v squared, yeah. Then my drag force would be equal to some constant and then like v squared, okay. Whichever assumption you use, that will be depending on like how you understand this system, and this understanding of the system come from experimenting with this system and doing a lot of empirical studies and experimentation in order to know and understand the governing relation of your system. For our case, let's just assume for simplicity, yeah, uh, that my drag force is proportional to velocity, and I have some drag coefficient here. So k here, that would be my drag coefficient. And what would be the unit of this drag coefficient? Like we can know this. So velocity, you know, the unit of like length over time, and so the drag coefficient need to have the unit of mass over time. Yeah, because force is mg. Like remember, force, this is like mass, and g, that is like L over t squared, acceleration due to gravity. So here the drag coefficient will have a unit of m over t. Okay, that would be the unit of this guy. Okay, so now I can put like in my equation here. So I can assume that this is like the z direction. So this is like positive in this direction. So if this is positive in this direction, so this guy will be like negative. So I have negative kv plus this guy here will be positive plus mg, my gravitational force, time my mass, time acceleration, and that would be dv over dt. And acceleration, I'm assuming, is positive. Yeah. So, wow. I was able actually to find something that looks like this. Is this like, does this look something familiar? Did we study this before? Yes, this is a differential equation. Let me arrange it and make it look a little bit nicer. So I can say like dv over dt. I can divide this is equal to g negative uh, kv over k is a constant. I mean, I can just call it a c, maybe better, be easier. Let me just call this constant here. That's a constant, yeah. So c over m. Okay, so now I have an equation. And this equation basically, it like, see, this is a differential equation. Why is it a differential equation? Because I have the function v and its derivative. Remember, that's the definition of a differential equation. You have a function v and its derivative. So that's a differential equation. And this differential equation, if I was able to solve it, it will give me velocity as a function of time. But how to solve it? We know how to solve this. We can solve it either analytically or we can solve it numerically. So we know how to solve this analytically from what we learned in calculus before. So in next video, I will show you, like, we will practice. I mean, there's nothing new. We solved like these types of guys before. So in the next video, we will learn how to solve this guy. Analytically review, not learn, like we will review how to solve this guy analytically, and then we will learn how to solve this guy numerically, which is a new part. Okay, so just to review, okay, so we have this. So just to review like what we did before. So here we have like a mathematical model. This is my dependent variable. These are my parameter, like this constant and mass, like how heavy this object, so that be the weight of the man and the parachutist. And then, so this is again my dependent variable, and here these are my forcing. So my forcing here will be acceleration due to gravity. And subject to initial condition, like the velocity at time zero, for example, was equal to zero or something like this. That's like my initial condition. Because remember, like to solve this analytical, this differential equation, you will, when you solve it, you will have a constant, and then like for this constant you need like initial or boundary condition to find this constant. So this is my initial condition. Yeah, so next video we will learn how, we will not learn, we already know how to solve this guy analytically by integrating this function, and the new part will be how to solve this guy numerically, and then I will compare the analytical and numerical solution. So analytically and numerically, and this is like a homework problem, which should be easy. Yeah. Okay. So see you in the next video.